So the informal definition of continuity says any function f of x whose graph can be sketched in one continuous motion without lifting the pencil is a continuous function. Basically, there's no breaks, there's no gaps, there's no jumps in the graph. You can put your pencil down and write all the way through the entire curve without lifting up your pencil. That's continuous. All right, so here's a second example, which is showing you an example that is not continuous, which is called discontinuous. So here's an example of what's called removable discontinuity. Why is it called removable discontinuity? Well, first of all, there's a hole in the graph. So remember that. So if there's a hole in the curve, it's called removable. The reason it's called removable is because we can actually remove the discontinuity. For example, in this particular example, if you let f1 equal 3, as defined, that would fill the hole, and then it would be continuous. So we can make this a continuous function by filling the hole. Well, the hole basically makes it a discontinuity. That's why it's called removable discontinuity. So once again, if there's a hole in the curve, it's called removable discontinuity. Okay, here's another example of a discontinuous function. This is an example of a jump discontinuity. I think you can figure out why they're calling it a jump discontinuity. So you can see there's a gap there, and because there's a gap there, right here, it's almost like the curve's going and then jumps to the next part of the curve. That's why it's called a jump discontinuity. Here's our third example of a discontinuity. This is example 4 because example 1 was basically showing you a continuous graph. But anyway, here's our third type of discontinuity. This is called infinite discontinuity. I think you can figure out why it's called infinite discontinuity because as the curves are going, they're both approaching an infinite number, which you can't really get to, right? This is why this is an example of an infinite discontinuity, This last example is our last discontinuity. It's sort of a rare one. You don't really see very often. It's called an oscillating discontinuity. So what are the 4 again? We got removable, we have jump, we have infinite, and we have oscillating. Removable, jump, infinite, and oscillating. Now I gave you an informal definition of what a continuous function actually is, what it looks like. This is a formal definition. It's a function that's continuous if and only if, and that's what the IFF stands for, if and only if, the limit as x approaches some magic number from the left of a function equals the limit as x approaches the same magic number from the right, which is also defined at that number. Remember, it can't have a hole there, so it has to be defined at that actual number as well for it to be a continuous graph. Left-hand limit equals the right-hand limit, which also equals the function's value. That means it's continuous. Now, here's an exception right here. You can have a left or right-hand endpoint, and that is considered continuous at that point if it is solid. All right, so is this function continuous everywhere? Is this function continuous everywhere, yes or no? Well, we got an endpoint here, solid, beautiful, and it goes, and then, we got a hole right there. So it's not really a true endpoint. So this is not continuous actually everywhere. You'd be like, nope, sorry, it's not continuous because of our situation with the open circle at the end. All right? Cool. Okay, let's check this example out. Is y equals the absolute value of x, that graph, or that function, continuous throughout its entire domain? So you got to know what the absolute value of x looks like. Again, another parent function to know what it looks like. I mean, I can draw it in there if you'd like me to, but otherwise think about what it would look like. Then hopefully y'all know what this looks like, but I'll draw it in real quick. So there you go. Not an ideal picture, not perfectly straight, but you get the idea behind it. It's supposed to be a V, and it goes on forever in both directions, and it never is broken. So yes, this one is continuous throughout its entire domain. Yes, for sure. All right, sweet. Is the function f of x equals sine of x over x continuous throughout its entire domain? Well, first of all, the answer to that question is no, because if you think about that, you can't divide by 0. We have an issue with that. So x can't be 0. Okay, we got that. And then what would it take to make it continuous throughout its entire domain? Well, remember how we talked about what's the limit as x approaches 0 of sine of x over x? I wanted you guys to memorize that. So again, the limit as x approaches 0 of sine of x over x is 1. So I'm going to draw a graph of it over on the right, and then we'll talk about how we can complete a piecewise function over there on the left side. All right. Now again, the picture's not perfect. You get the idea behind it though. So what would it take to make it continuous throughout its entire domain? Well, if f of 0 equaled 1, then it would be continuous, right? Because right now, x can't be 0. So if f of 0 was 1, it would work. So let me show you how you'd write your piecewise function. All right, so now if you look at that, I have a piecewise function. The first piece is sine of x over x, where x does not equal 0. And then to complete it, to make it continuous, I have the second piece of the function where I say f of x is 1 when x is 0. That now is a continuous function. This process is called a continuous extension. So I've figured out how can I fix it. And if I can figure out how to fix it, then you'd write it out as a piecewise function, and it's called a continuous extension. There you go. So checking this one out, it says for g of x equals the quantity of x squared minus 1 over x minus 1, where x is 1. It says give a formula for the extended function that is continuous at the indicated point. All right, so we got to try to come up with a piecewise function that works for this. Because right now, if x is 1, we have an issue. Because looking at the denominator, 1 minus 1 is 0, and you can't divide by 0. So we have to give a formula for the extended function that is continuous at the indicated point. Okay, so I'm not done. I just have it set up as a piecewise function. You can see the top piece is the original function given, x squared minus 1 all over x minus 1, and then I put that, well, that works for x not equal to 1. Okay, we have that situation. But then the question is, what happens when x is 1? So what would the y value become, or in this case the g of x value become when x is 1? Well, if you look at and think about the piecewise function, what we had to do with the piecewise functions, let me show you what I'm talking about here. Checking this out. Remember, you can rewrite that. Remember how we'd always try to factor before we do anything with rational functions? So if I factor this, like that, and we'll do this right down here. Now if you look, you can cross out the common factor right there. What do you have left? We have x plus 1 left in the numerator, right? That's what's left over. Well, that's the second piece that works for us. So I could write it now as, let me get my blue here, right here, x plus 1. Where x equals 1, the other piece that works for us is x plus 1. Again, seeing what I just did over there up on the right in green, where I crossed out common factors. Now you can see that actually is a piecewise function that is continuous. So I could ask you, if x is 1, I mean, what would happen here? If x is 1, that would become 2, wouldn't it? I mean, I could write 2 here. I could write g of x is 2 when x is 1, but I figured I could just write the actual expression right here because that works. So this is the original. X couldn't be 1 because you can't divide by 0. And then this is the new one I have that works because with this, where x is 1, this actually completes and makes it a continuous function. And there's a picture of the piecewise function. You see the open circle there at 1, 2. That's from the first piece. And then I could fill it in. I mean, literally fill it in because I'm adding a second piece. So I can try to fill in this hole right here. Okay? There you go. Here's your completed example. All right, so let's check out this example. So it says, what value must k be equal to such that f of x is continuous at x equal 1? So we got to figure out where is that y value where when I graph this piecewise function, there's no hole in the graph. Like these are connected, all right? So instead of graphing them, which you could graph the parabola, if you look at that and think about that, how we could just graph that with the vertex form if you want to do it that way. But then you can't really graph the line per se because it says 2x plus k. We don't even know what the y-intercept is. But our idea is to try and figure out what the y-intercept would be, whereas with the piecewise function here, they're connected. So I want to show you how we can do this algebraically. The thing is, we want to know what's the value of k at x equal 1, right? Well, think about the fact that I want to find where these two pieces meet. Where are those two pieces equal to each other? Well, that gives you the clue on what we're going to do. We're going to literally set each of these equations equal to each other. Equals 2x plus k. So we got that start. But then it says, what's the value of k when the x value is 1? Well, look at the equation I have right there. why don't we go ahead and plug and chug 1 in for the x's? Literally, 1 squared minus 2 times 1 plus 1 equals 2 times 1 plus k. There. And now let's solve for k. Looking on the left side of the equation, 1 squared is 1, minus 2, which is negative 1, plus 1, which is 0, equals 2 plus k. How do you solve for k? Subtract 2 from both sides. And we end up with k equaling negative 2. And that's the value of k that would actually make that piecewise function continuous. Now I'm going to go ahead and graph these. I'm going to graph the parabola and I'm going to graph the line. Now that we know that k, or the y-intercept, is at negative 2, I'm going to graph those two and show you what's going on, what happens. So what I did was I graphed the two pieces. I graphed this parabola here, which was basically, if I took that and factored it, it would be the quantity of x minus 1 squared. So I just shifted the parabola from the parent function of x squared, shifted it to the right 1. And then it was x is less than 1, so I'd have an open circle there in blue. Then I graphed this line. Remember, k is negative 2, so I start at negative 2 on the y-axis as my y-intercept. I went up 2 over 1. Up 2 over 1. Now I apologize, the line is a little wavy. It's just, so you can see then what would happen is, here at x equal 1, you can see that it would be a filled in circle now at that point right here. So we got that. So that's why the k would have to be negative 2 for you to be able to graph the line that makes this a continuous piecewise function. Alright? Cool. Alright, let's check this out. So it says use the graph to answer these questions. First question, does f of 3 exist? Does f of 3 exist? Is there a point defined when x is 3? Yeah, it is. So f of 3 exists, yes. Matter of fact, we can say where. It exists at, what? The point 3, 1. Right there, you see the dot right there at 3, 1. That's where it's defined. Next question, does the limit as x approaches 3 exist? So the left-hand limit, right-hand limit, are they coming in to be at the same location? Yeah, they are actually. So the limit of as x approaches 3 does exist. So I'm going to say yes to that one as well. We can also say it's at, what do we got there? 3, 2. I know the point's not defined at 3, 2, but the limit exists at 3, 2, because that's the intended height. Okay, does the limit as x approaches 3 of f of x equal the same as f of 3? Does 1 equal 2? No, it does not. So then, is f continuous at x equals 3? Nope, it's not. So you got that removable situation right up there, that open circle there. And then here's our statement once again. A function y equals f of x is continuous at an interior point if it's of its domain, if, again, the limit as x approaches that number is the same as the point defined at that number. Alright, so it says sketch a possible graph for a function f that has the stated properties. So f of 4 exists, but the limit as x approaches 4 does not exist. So let me see what we got. Well, if f of 4 exists, I need a point there when x is 4. So I'm just going to randomly put a point right there. So there, f of 4 exists. You can see the blue dot right there. So that's good. Then the limit as x approaches 4 doesn't exist. Okay, then I can just draw, I guess I'll use red. And I'll just draw something coming in like this and just go like that. And I'll just put an open circle right there, hanging out right there. And there you go. There. We got it. So that's just an example where the limit as x approaches 4 doesn't exist. Got an open circle there. Left-hand limit doesn't equal the right-hand limit. Plus f of 4 does exist. Now looking at the bottom, it says find a value for a. Find a value for a such that or so that the function is continuous. Well, where is it trying to be continuous? It's trying to be continuous at x equals 3. So if you remember what we did here, we basically set each expression or each equation equal to each other. So x squared minus 1 equals 2ax. And then, remember, I'm trying to find the a value when x is 3, so I can just plug in 3. So we got what? 3 squared minus 1 equals 2 times a times 3. So on the left side, 3 squared minus 1 is 8. On the right side, we got 6a Solve for a, divide both sides by 6. Final answer, a is 8/6, or reduce it, of course, to be what? 4/3. Yep, a is 4/3. There you go. Awesome. All right, last example. Whew. Give a formula for the extended function that is continuous at the indicated point. All right, so if you recall, we're going to make piecewise function. We're going to set this up as a piecewise function, f of x equals. Okay, so let's see. First thing is, let's go ahead and put the first equation here, x squared minus 9 over x plus 3. And the fact for this one, x cannot equal -3. Because again, looking at the denominator, if x was -3, it'd be divided by 0. That doesn't work. Now, what do we have left? How can we fix this? Well, remember, we're going to come up with something where x does equal 3. So what happens here? Let's see. Let's find out. Let's go ahead and take the function itself. And we'll take this guy and let's go ahead and factor this out. So we have what? X plus 3, x minus 3 over x plus 3. X plus c's cross out. Boom, boom. So all we have left is that expression of x minus 3. So there you go. That is our extended function that now works. That makes it a continuous piecewise function right there. Cool, cool. Sweet.